All right, hi guys. My name is Juan Rosas,
Hello everyone, my name is Jonathan Rosas.
and our presentation is going to be on methods for true energy performance optimization.
Okay, so to begin, we're gonna just be going over like an overview of the paper. Um, so the whole purpose of like the paper was to kind of analyze the true optimization between energy and performance at the chip design level. Um, so some of the key concepts that we went over in the paper had to do mostly with optimization, but some of the things that we kind of noted down is that optimization can be traded off by the following: gate size, supply, and threshold voltages. And in terms of optimizing what's it called, optimizing chip design, it's really important to balance gate size, supply voltage, and threshold voltages to actually achieve optimal design. And also some of the two things that were really key in the paper was parallel and pipeline design. Both of them having their own pros and cons. And we're going to be talking more about those exact pros and cons of parallel and pipeline designing throughout the presentation. So in terms of performance, the performance against energy, there's some key concepts that we noted down. One of the biggest things that we had to talk about is power dissipation, since it is the primary limiting factor in chip designs in today's world. Correct optimization either minimizes energy consumption or maximizes the amount of computation. And something else we have to kind of note also is that energy efficiency is the key in achieving high performance. And optimizing every layer in chip design does not always equal optimal design. We're going to be talking all more about exactly what this means throughout the presentation. And finally, optimization is performed in three layers, and those three layers are going to be discussed in the next slideshow.
Yeah, so kind of like my partner Jonathan was talking about, we will be focusing on three layers, and we'll be looking within each layer. So to begin with, how is it that we're able to achieve energy performance optimization? Um, and as we stated, it would be through these layers. First being the outermost layer, which is the system architecture optimization. That one focuses on process of designing, configuring, or refining overall structure and components of systems to achieve optimal efficiency. One layer in would be the microarchitectural optimization, which is optimizing the design and organization of the processor's internal components, such as execution units, pipelines, and cache. And the innermost layer being the fixed circuit topology, um, so it's specific and static arrangements of digital logic components within an integrated circuit or digital system. The arrangement is designed to efficiently perform a predefined set of functions or tasks for both efficiency and performance. So what we will be doing is just talking about certain concepts within them to improve the overall optimization and performance.
So the first level that we're going to be talking about is the system architecture level. So some of the key concepts that we have to talk about is performance optimization and power optimization. When we're talking about performance optimization, there's two things that I have to talk about. Is clock frequency and pipeline depth. So in terms of clock frequency, increasing the clock frequency can boost performance, but overall can generate high power consumption, which can affect the chip overall. And in terms of pipelining depth, changing the depth of the pipeline will affect the throughput and latency of the circuit, which could have a positive output or a negative output. But that's why, in terms of pipeline depth, you have to find a right balance to truly achieve optimization. And in terms of power optimization, we have to go over some of the techniques that are used at the system level, which is power gating and dynamic voltaging and frequency scaling. And overall, like we had mentioned, in terms of power optimization, the goal is to optimize power usage while meeting performance requirements. Two other concepts that we have to focus on as well is functional components and interconnectional architecture. So when we're talking about functional components, we're referring to processors, memory units, and input and output interfaces. So in order, as a chip designer, you have to really analyze like how many processors you're gonna have to include, what size you're gonna have to include, the type of memory you'll be using, or if you're gonna have to use any specialized hardware components. This overall has a really big impact in terms of optimizing your chip. Um, and then when we're talking about interconnectional architecture, this basically refers to how are each components communicating with one another, how is data being shared. So in terms of optimization, you have to really look at how you could optimize efficient data transfer and how you can have a low latency and a high bandwidth.
Yeah, so now we're going to focus on the intermediate layer for the microarchitecture optimization part. And we're going to be specifically focusing on pipeline design. So a quick overview on that would be that pipeline is a key component of a central processing unit that allows multiple instructions be processed simultaneously in different stages, improving overall performance. So essentially, what they do is they store the information from the instructions and calculations so that the logic gates of the next stage can do the next steps. One way that we're able to improve is by the length of the pipeline. One of the advantages for this is that if we create a longer pipeline, that can potentially increase instructions throughput by allowing more instructions to be in different strategies of execution at the same time. One of the downfalls, though, would be that the longer the pipeline, that can also lead to increased latency as it takes more clock cycles for an instruction to traverse the entire pipeline.
So, like we had mentioned, one of the methods for designing is pipelining, but there is also another design called parallelism. So parallelism is when you're simultaneously executing multiple instructions at the same time. And in terms of energy efficiency, it is far more efficient to do um, parallel design rather than pipeline design. And something that you should note is that parallelism decreases the amount of time that a device spends on computation, which increases the ratio of wasted energy to useful energy, which overall obviously improves optimization.
Yeah, so once talking about the innermost layer being the fixed circuit topology, we're going to focus on the efficient logic arrangements. Again, a quick overview is that strategic organizations and layout of logic gates within a circuit to achieve desired performance goals while minimizing the factors like power consumption and signal delays. Overall, we're just trying to um, it's basically techniques used to reduce the number of logic gates required to implement a given logic circuit by improving its efficiency and reducing its complexity. So we're going to be focusing on minimizing the signal paths. Can you go back, please? So once we talked about, like I said, minimizing the signal paths, is that the pro of it would be, the shorter paths generally result in reduced signal propagation delays, which will overall improve the circuit speed. Again, one of the downfalls, though, would be that since it is a shorter path, congestions may occur in areas of where the chip have limited routing resources, which can make it difficult to meet timing constraints and may require additional design iterations. Another thing we can focus on is the minimized redundancy, where that's the effort to eliminate unnecessary or duplicate components, connections, or functionalities within a given circuit design while maintaining its functionalities. Some of the ways that we're able to improve from this is to reevaluate the design constraints, right? To review the design constraints to ensure that they align with the current project at the moment. You can also reuse components, where reusing components within the circuit where applicable can reduce the overall number of components and simplify the design, as well as the functional block analysis, which would divide the circuit into functional blocks and analyze each block independently. So to conclude, these are some of the layers that were mentioned within the article for energy performance optimization. Again, being the system's architecture, the microarchitecture, and the fixed circuit topologies, and some certain concepts and procedures that you're able to take to improve on it. In essence, hopefully would, you know, maximize the energy efficiency and minimize the power consumption in the computing system overall. That's it. Thank you.
Thank you, Professor.